Alright, here we go with lesson 7.3. This shouldn't be too much of a stretch, especially you all seem to make the connection between congruency and similarity. So this really shouldn't be too big of a stretch for us. Just as with congruency, we had a number of postulates that allowed us to prove certain shapes congruent. So especially right now we're dealing with triangles, right? So when we talked about congruency, we talked about side angle side and side 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 and all those different postulates that allowed us to say, okay, if we have this information and this information, then we can say for sure, yes, these two triangles are congruent. Well, we have basically the same situation with similar triangles. So we're going to learn a couple postulates that enable us to determine whether or not two triangles are similar. The first one here is just angle, angle. And it says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. That's it. All we need are two angles. So in this case, T and P are congruent and R and L are congruent. And so we can say that those two triangles are similar. They could be the exact same triangle. They could be congruent if we were to find that all their sides were the same. But at the very least, they are similar. Even though we haven't checked any of the sides, that's the good thing about triangles, is that we don't even most of the time have to check the sides if we have enough information. In this case, if we have two angles, we know that they're going to be similar. We don't even have to look at the ratio of the sides to see if it works out, because it will always work out that way. So now it's just a matter of writing the appropriate similarity statement. And we can see that this one is written as TRS, so T, then R, then S. And so we need to line up the appropriate angles. T corresponds to P, R corresponds to L, S is going to correspond to M, and so we get PLM. So moving on, two more postulates. Well, these ones are theorems, but you get the idea. So side angle side, just like we talked about with congruency, there's a side angle side congruency theorem. There's also a side angle side similarity theorem. And you can probably guess in this case, the angle, again, the angles have to be congruent, but our two sides that make up the angle, instead of being congruent, they're just going to be proportional. So if we can show that the two sides are proportional to the corresponding sides on another triangle and the angle that they make is congruent, then we can say that those two triangles are similar. And we'll see some examples of that later. And then finally, the last one, side, side, side. Again, instead of saying that the three sides are congruent of a triangle, if we can say that the corresponding sides have the corresponding sides are proportional, then we can say that those two triangles are similar as well. The last thing that they throw in here is this idea of indirect measurement, and they give kind of a hokey definition. Indirect measurement is a way of measuring things that are difficult to measure directly. So if you can't do it directly, you do it indirectly. But it still doesn't really tell us exactly what it is. There's a number of things that you might need to measure indirectly. For example, if you had a basketball court and you were going to excavate it, right? You were going to take the whole court out, trash it, and you wanted to know how much concrete was in that basketball court. Well, you don't really have a scale to pick it up and put the entire basketball court on a scale. It's kind of silly. But you could say, all right, well, I know that the concrete is, 1 foot deep, and I know the dimensions of my basketball court in feet, this many feet, or meters, or however you measure it. You could take one, let's say 1 square foot of that basketball court, and you could measure the weight of that, and then you could just expand it out. Well, I know that my basketball court has 150 square feet in it, or whatever it happens to be. Then you can expand it out. You're indirectly measuring the mass of the whole basketball court by looking at the mass of a smaller area of it. Another way that they do this, they like to show these problems where you use similar triangles. So, maybe you can't measure something bigger, such as a giant monument, but you might be able to measure something smaller, such as a scaled down model, or even, something that's sitting beside it, as long as you can show that the two are similar. So we're going to see some examples of that as we go on as well for indirect measurement. The first example, we're using the angle-angle similarity postulate. They give us a figure over here, and they tell us that MX is perpendicular to AB. So that's good, because then we know that these two angles, MXA and KXB, are going to be 90 degrees. Right? So if these two angles in here are 90 degrees, they also tell us that 58 and 58, so we've got two angles in there. So because these are perpendicular, we can say that those are right angles, so they are congruent. And then we can also see, just based on the labels, that A and B are congruent. Therefore, using the angle-angle similarity postulate, we can say that the two triangles are similar, not congruent. Obviously, this one is much smaller, but they are similar. Moving on with the next example. Using some more of these theorems, it says explain why the triangles must be similar, and then write a similarity statement. So this is getting at the first thing we should notice over here is that when we have two intersecting lines like this, we can always indicate that the vertical angles are congruent. Right? So we've got congruent vertical angles there. So it says YVZ, right? YVZ is congruent to WVX, and we know that. We said those are vertical angles. That's our vertical angle postulate or theorem, if you will. So we've got congruent angles here, and then we can see that we do have measurements for the sides that make up those angles. So if we think back to the postulates and theorems that we learned for this lesson, we do know there is a side angle side, but we have to show that the sides are proportional. So first they're going to look at VY and VW. So comparing VY here and VW. Now you might say, well, why don't they compare this one to this one and then the top two? Well, we could do that, but if you look, we've got 12 is smaller than 18, and 24 is smaller than 36. So if we're going to compare the two sides, we better compare the smaller one here with the smaller one here, and then the larger one here with the larger one here. So if we compare 12 and 24, VY and VW, that's a ratio of 1 to 2, right, or 1/2. So now if we can compare the other two, VZ and VX, 18 to 36, that's again 1 to 2 or 1/2. So corresponding sides are proportional and the angle that's included are congruent. Therefore, using side angle side similarity theorem, we can say that the two triangles are in fact similar. And then for our last example, we're going to get into a little bit of this indirect measurement. So here, Joan is represented by JO right here, this vertical line. So that's the body of Joan, this person. And TR over here is represents a tree. So it says Joan places a mirror 24 feet from the base of a tree. So here's the mirror at point M on the ground, and it's 24 feet from the base of the tree. She says, and it says when she stands 3 feet from the mirror, she can see the top of the tree reflected in it. So here's the mirror, she's 3 feet away, and as she looks down at the mirror and the image bounces back up, the reflection, she can see the top of the tree. It says if her eyes are 5 feet above the ground, so this J doesn't necessarily represent her head, it represents her eyes, which are looking down into the mirror and up to the top of the tree. It says if her eyes are 5 feet above the ground, how tall is the tree? So we have TR, we've got JO representing our tree and our Joan. And we know that both of them, we can see the right angles here as they're marked, but also if you think of a tree, it should be standing straight up. A person should be standing straight up if they have good posture, I guess. So both of them are going to be perpendicular to the ground, right? Joan is making a right angle with the ground, the tree is making a right angle with the ground. Now, the other thing that we need to bear in mind, so if we know that they're both perpendicular, we know that those two angles are congruent, right? JOM and TRM are both going to be congruent, right? Both are 90-degree angles. Now, the last thing that we need to note, and this is maybe mixing a little bit of physics in here, but if we have a light ray or an image that bounces off of a mirror, they say the saying is the image of reflection, or sorry, the angle of incidence is equal to the angle of reflection. Meaning whatever angle you're looking into a mirror, see this angle down here, is always going to be the same as the angle that bounces back. So based on the fact that this is a mirror, and this is someone looking into the mirror and the reflection that they're getting, we can say that this angle and this angle are congruent. Just based on the fact that when light reflects off a mirror, it always reflects back at the same angle. So we know that these two angles are going to be congruent as well. So we now have two angles that are congruent in our two triangles, so we don't even need to look at the proportion of the sides. Right? We can just go straight ahead and say, using the angle-angle similarity postulate, that those two triangles will be similar. Make sure to write it correctly, right? J-O-M and then T-R-M when you write the similarity statement. Now, if we look at these, what are we trying to find? The question wants to know how tall is the tree. Well, that means we want to find this length here, TR. So if we're going to set this up, we can set up a proportion. We know that TR corresponds to JO, right? TR and JO in our two similar triangles. And then we can use the two other sides. OM is going to correspond to RM. So we can set up those corresponding sides of the similar triangles, and we can set up a nice proportion here, and then we can plug in what we know. We're trying to find TR, but we do know that JO is 5, RM is 24, and OM is 3. From there we should be able to solve, just multiply by 5. We bring the 5 over to the other side, and then once we simplify that down, we get TR is 40. So the height of our tree should be 40 feet. So that's one of those examples of indirect measurement where we don't really have a tape measure that can run up to the top of a tree and it's kind of dangerous to climb, but we can use a mirror and just a little bit of geometry know-how to measure the height of a tree. And this is, it's kind of a simplified version, but this is what land surveyors do. They use angles and distances and indirect measurement and things like that to measure land and block off territories and things like that. So interesting little application. All right, from there, as always, you guys are free to hit the quick checks. Go ahead and give those a crack for homework, and we will pick up from there and check those out in class tomorrow.